Hello, ladies and gentlemen. Buckle up your seatbelts. This is going to be a long one. We are covering two sections today. Similarity transformations and similarity within triangles and proving triangles similar. So first of all, we're going to look at performing a composition of rigid motion. So way back, many units ago, we learned how to do composition of motions. And you learned that we are going to work from right to left. So we want to perform this dilation first. So we're going to dilate ABC by 1/2. So if we have our coordinate A, 2, 4, we're going to multiply each of those coordinates by 1/2, giving us A prime of 1 and 2. Okay, this will give us coordinate B prime at 1/2 of -2 is 1, and 1/2 of 8 is 4. Our 1/2 dilation for point C will be 0, of course, and then 5. So 1/2 is 10 is 5. So I'll plot each of those points, 1, 2 for my A prime. I'll get my B at -1, 4, my B prime, and then my C at 0, 5 here, my C prime. And then that will be my triangle with my dilation. Remember to be sure when there's no center of dilation indicated there, that means we are dilating with the center point at the origin. Okay, so now I have my triangle here, got my new triangle here. Now we're going to reflect it around the line x equals -3. Okay, so now I'm going to take my points and reflect them around the line x equals 3. So point A here is 1, 2, 3, 4 away from the line. So it's going to be 1, 2, 3, 4 away from that line. And that will give me my new A. We'll call that A double prime. Okay. My next point B is 2 away. So it's going to be 2 away on the other side. And we'll call that point B double prime. All right. Up here, this one is 3 away. And it will be 3 away over here. 1, 2, 3. I'm going to call that one C double prime. All right. And then if I connect all my dots there for that guy, and this time I'll make them a little straighter than I did on my last one. A little crazy. C to C, B to B, and A there. I have my A prime, B prime, C prime. So that is my composition of rigid motions here. Okay. All right. So here's another one, and you might want to pause this and just see how you do and do it on your own. We're going to first rotate 90 degrees about the origin here, and then dilate it by 3. Okay, so here's my coordinates here. As a reminder of when I rotate around the 90 degrees around the axis, we're going counterclockwise. The new coordinates are going to be opposite of y, x, right? So my x is going to be -5, 3. So we can take over here -5, 1, 2, 3. That's my new coordinate x prime. So y is going to be -4, -1. I'll plot that here, and that will be my y prime. And then my z will be -7, 1. So come out here to -7 and 1, and that will be my new z prime. And so again, I can take my, go ahead and get my little line maker here and create my triangle. Connect all my dots to get my triangle. So that's my x prime, y prime, z prime. Now the next thing I need to do is I need to dilate it by 3. Okay, so I'm going to take all my coordinates here. So I'll have my x is at what? -5, -5, 3. So my x prime is at -5, 3. And so if we dilate that by 3, that's going to give us a -15, 9. That's going to be my x double prime. Okay, my y prime is at -4, -1. -4, -1. And that's going to go to my y double prime. We're going to multiply each of those by 3. So -12, not -3 by 3, -3. My z prime coordinates are at -7, 1. So my new coordinates there are going to be z double prime, -21, and 3. I hope I have enough room for that. I think I do. Okay. So we're going to go with x double prime is going to be -15, 9 up here. That's going to be my x double prime. My y double prime will be at -12, 9. Oh, sorry, -12, -3. My bad. -12, -3. That's going to be my y double prime, and my z double prime is going to be at negative 21, 3. 1, 2, 3, and that's going to be my z double prime. And so I can connect all my points there. Grab my green and connect all my points to my triangle. And I'll have my triangle x prime, double prime, y double prime, z double prime. So that is my rotation of 90 degrees followed by a dilation of 3. Okay? All right, so now we're going to just describe a composition of rigid motions. Now on these ones, I'm going to just kind of take us into a program here. I got to bring it over here. I don't know why it's not opening on my screen. And so what we want to do here, hope it'll load quickly. Tick tock, tick tock. Don't forget that. So what we're going to do, I'm just going to pull it up over here. Okay, so what we're going to do here is they appear to be the same size and shape, but how do we get them to be there? Be the same size. We're going to prove it by just describing a rigid motion. So first of all, I'm going to rotate. I can rotate my triangle around 180 degrees. You kind of see this rotation right here, 180 degrees. And after I rotate it 180 degrees, I can then dilate it. A scale factor of 2, and that will put it on, make it a exact. Right, exact. So that's how I can kind of map it and say, yes, it is similar because it has 2 rotations. Now, another thing I can do, by the way, is I can first dilate it up here, boom, and then rotate it. So rotate it around 180 degrees, and boom, we're too far. Right there, and I'm still on the same figure. Okay? And so that's how I can describe that particular rigid motion, the dilation of 2 and then a rotation of 90 degrees. Okay. So right here, note that I can dilate and then rotate, I'll have the same result. However, that doesn't always happen. If I translate and then rotate, I'm going to end up with a completely different location for my triangle. So be careful with that. I cannot translate and then rotate and then do the opposite and have it be the same thing. Okay. All right, so a similarity transformation is a composition of one or more rigid motions and a dilation. Okay, so that because a dilation makes it similar, because it makes it bigger or smaller. So it's a composition of one or more rigid motions and a dilation. A similarity transformation results in an image that is similar to the pre-image. Okay, so it's a similarity transformation. So why is PQRS similar to GHJK? So first of all, one hint to look at here is if I look at angle S, it corresponds to angle H, but then also angle P corresponds to angle G. You can kind of see that. P is on the right-hand side of S, but G is on the left-hand side of H. So we know that there has to be a reflection there. So that's why it says check angles and note that the orientation is reversed. So we want to make sure we reflect there. Then we can kind of translate it till the points are aligned and then dilate it. Okay. So I have another little figure here. I can kind of show this to you with it. So we're first going to reflect it. Boom. So it kind of reflects up here. And you don't have to do this. This is just basically describing. Okay. And then we're going to translate it. So it kind of sits down here. So it goes over the line M, then it's translate down here until H is lined up. And now I'm going to dilate it to where it fits that figure. Okay. And that's how you do that one. So we're just going to describe that. We're going to reflect it. Then we're going to translate it onto the figure, and then we're going to dilate it. Okay. So how about this one? What are we going to do with this one? Again, if I look at X and X down here and Z, they're kind of flipped, right? So we know we're going to have to first flip it. We're going to have to first somehow, reflect it over some line that's going to make it flip around. And then we're going to have to translate it and then dilate it. Okay. And that's all you're going to have to say. So what I have to do is I'm going to have to reflect it, reflect the image. Then I'm going to have to dilate it. Or excuse me, we're going to have to first translate it. My bad. We have to translate it, get it on top of each other. And after we get that done, we'll get the points X and X lined up together, or Z and Z. Then we can go ahead and dilate it from there and get it to match up. Okay, so that's all you need to do for this part, is just be able to kind of describe what you're going to have to do to get those similarity transformation. Okay, so that kind of wraps it up for that section. Now we're going to kind of go into proving similar triangles. Okay, so this is kind of like our proving triangles congruent, except that these triangles are similar. They're not the same size. So we have 3 different triangle similarities. One is an angle-angle similarity postulate, which basically says if 2 angles of one triangle are congruent to 2 angles of another triangle, my 2 triangles are indeed similar. Okay. This one is a side-side-side similarity, which says if all of my sides have the same ratio. So remember, for similarity, they have to have the same ratio, not equal. They have to have the same ratio. So if all 3 of my sides have the same ratio, then the 2 triangles are similar. Okay, so these ones have all the pink ones, and the green ones and the orange ones all have a ratio of 1.25. And then the last one is side angle side. That says if I have 2 sides that are proportional and an angle between them that are equal, then my 2 triangles are similar. Okay, so we're going to start putting some of these to use here. So are triangles ABC and DEF similar? So again, just like in congruence, we want to make sure that we kind of look at these segments that are corresponding. So we know that AB corresponds to DE, right? So 3 over 4.5. We're going to test that one, right? So 3 over 4.5. We also know that BC corresponds to EF, right? So BC corresponds to EF, so 4 over 6. And then we also know, excuse me, that AC corresponds to DF, so 5 over 7.5. So the question is, are all those the same ratio? Well, 3 over 4.5, 3 divided by 4.5 is 0.67. Okay. 4 6 is 0.67, right? How about 5 over 7.5? So 5 divided by 7.5, that is also 0.67. So this is yes, right? ABC, triangle ABC is similar, and that's my symbol for similar is a little squiggly line. It's a tilde. Is congruent to triangle DEF. And not congruent, I'm sorry, similar. Triangle ABC is similar to triangles DEF. Okay, and that is by side, side, side similarity. Okay. All right, let's move on to the next one. So these are kind of overlapping. So our PQS and PQ are similar. Now the biggest mistake here is everybody wants to say PQ over PQ, but that's not the corresponding sides. Notice that PQ corresponds to RQ. So it's super important here that you separate these triangles and get them corresponding to the sides that they need to correspond to. Okay. So I separated these out here and I put them in, PQS and PQR. So I kind of put them in the position that they correspond. And I labeled their sides 18, 27, and 12 and 18. Okay. They have an angle between them. They share this angle Q, right? So they have this angle Q already. So we're looking at side angle side similarity so long as those other sides are proportional. So as 12, we're going to look at 12 and 18. So 12 over 18, we're going to look at that ratio. And then we're also going to look at this 18 and 27. So 18 over 27. Now I'm doing the small triangle to the big triangle. Okay. So that's important. Also, make sure you have to keep that same ratio. You could do large to small as long as you're doing it the same. So I'm doing the small triangle to the large triangle. Okay. And so I'm doing 12 over 18 is 0.67 again. And then this ratio here, 18 over 27, is also 0.67. And then we also have our congruent triangles. So yes, these are similar. So triangle PQS is similar to triangle RQP, and that is because of my side angle side similarity. Okay. So here's another one. You might want to try to do this one. Try to separate these triangles. ADE is ADE congruent to BDE. So if you look at the triangles here, ADE is this one right here. Whoops, I can't draw on that one. I pull it apart. ADE, this is the one we're looking at right here. Is that similar to ABD, this bigger triangle here? So you might want to pause the video, see if you can do that on your own. Okay, so these are the 2 triangles right here. I kind of pulled them apart and wrote all the vertices and the measurements on them. So in other words, we need to kind of look and see if we have, it's 1.8, the same ratio, 1.8 over 2.4. And we have the same one twice, right? 1.8 over 2.4, is that the same ratio as 2.4 over 3.2? 2.4 over 3.2. So first of all, that 1.8 over 2.4 is 0.75. And then we have the 2.4 divided by 3.2 is also 0.75. This other one's the same one, so we don't need to calculate that one again. So yes, it is. It is similar. And that is because of, we have side, side, side. Side, side, side similarity. Okay? Okay, so now we're going to find values. So when they tell us that it's already similar, we know it's similar. So we can use the fact that the sides are proportional to find missing sides. So what we look for here is the sides that we know that correspond. So I know that BA here corresponds to DE over here. So I can use that proportion, that 6 over 21. We know that, right? So we're going to use that to set up the other values. So that equals, and I want to find X. So I want to know X. So I'm going small to big again, by the way. So I want to make sure you all know that. So I'm going small to big triangle. Okay. So I'm going 6 over 21 equals X over, and then I need to find what X corresponds to. That's AC right here. So I need to find DC, right? So this is my DC right here, 28. Once I get that proportion set up, I can cross multiply. 21X equals my 6 times 28. So that's 21X equals my 6 times 28 is 168. And then I'm going to divide by 21. So X is equal to 168 divided by 21 is 8. So my value of X is 8. So let's do the same thing now for Y. So again, I already know my 6 over 21. That's going to stay the same. I need to figure out my value for Y. Okay, so that equals my Y is on my big one now. So keep that in mind. So that's going to go on the bottom. That's where my big one goes. Right? So it's small to big, small to big. You have to stay consistent. So that corresponds to which one? So CE right here corresponds to BC. Okay? So there's my BC right here, 10. So that's going to go on top because that's the small triangle. You got to make sure you keep those proportions the same. If you set up big to small, that's great. But up here is my small ratios. Down here are my big ratios, right? On both sides. So now I can cross multiply. I can do my 6y. 6 times y equals 21 times 10. So 6y equals 210 divided by 6. So 210 divided by 6 is equal to 35. And that's my value for y. Okay, so that's how you set that up. You just have to find a side that you have in common. You can set a proportion up with, and then make sure you keep them set the same ratio, big to small or small to big. Make sure you keep them the same on both sides. Okay. All right, now you try it. Go ahead and find MN over here. Okay, we want to find this length right here, X, and then come back and see how you do. Okay, so we know that these two triangles are isosceles, so it doesn't really matter how we set them up as long as you go big to small or small to big. Again, I'm going to go small to big. I just like that way. And so I'm going to say 1 over 75 equals, I'm going to go X over 10. Okay, so 75 times X equals 10 divided by 75. So X equals, what is 10 divided by 75 is a small number, 0.13. It's a little guy. Okay. All right, we have one more little application here. So Avery puts up a radio antenna tower in his yard. Ella tells him that the city has a new law limiting the towers to 50 feet in height. How can Avery use the lengths of his shadow and the shadow of the tower to show that the tower is within the city limits without directly measuring it? So we already know that, anytime we have the sun kind of casting shadows, we know that these angles are always equal there, okay? And so we know that we have an angle and we have this height here and the height here. So we need to see if we have some sort of proportion that we can kind of show we have, okay? We know that these angles casting down with the sun are always the same. So we have angle similarity. We need to see what the proportions are now. So I'm going to set up 5 over 10 equals, and it's going to be 6 over, we're going to call this X. So 6 over X it looks like it's a 1/2 proportion, right? So it should be 12. We'll go ahead and calculate it anyway. So 5 times x equals 60. So x equals 12. And it looks like that's well within the height limit. It's only 12 feet, so they are good to go. Okay? All right, so that is it. So that you might want to kind of take a minute just kind of looking at this. This kind of talks about our similarity transformations. And then down here, it has all of our similarity theorems, our angle similarity, side similarity, and our side angle side similarity. And make sure you have all those down in your notes. And then you guys have an Excel in Google Classroom. And then if you have any questions, please bring them to Zoom and I'll be happy to answer them. And I might be seeing you in school soon. All right, take care and I'll see you soon. Bye-bye.